Hello everyone and welcome to Atensifelon Lectures. Atensifelon is a research company that employs expertise in neuroscience and computer science with the intent of using a regular computer program to control the brain of a living animal. Atensifelon has advanced research in this field, and this series of lectures underscore our belief in this possibility. This is the third in our series of lectures. A link to the first two lectures is provided with this video. In this third lecture, we shall be designing logic circuits with neurons. So it's about designing logic circuits with neurons. At the end of the last lecture, we concluded that a neuron can express logic depending on the influence presynaptic neurons have on the membrane potential of postsynaptic neurons as measured at the axon hillock. We also looked at how a postsynaptic neuron could express and or all logic using spatial summation. And so we said in this series of lectures, we shall concentrate on spatial summation. The issue of temporal summation will be addressed at a much later video. So spatial summation only is what we'll be looking at. So this is a picture of a neuron, right? On your right-hand side. Has a soma, has axon terminals and all that. But for the purpose of illustration in this video, I'll be drawing them with what you have on your right-hand side. So the first place here we have A. That means I'm saying the name of this neuron is neuron A. The circle indicates the soma and the dendrites on that soma. So just the circle here will indicate that this is the soma and then dendrites are on that soma. That's what it indicates. This long protruding arrow from the base is the axon. So this axon goes all the way from the base of the soma all the way out, and that place where it contacts the soma is where we call the axon hillock. So it goes all the way here down, and that's where action potentials travel from. So we have branching from these axons. These axons are branching out. So these are called axon terminals. So this neuron A now has 1, 2, 3 axon terminals. We can also draw it this way, where we have, this is a neuron. This neuron expresses, when you see the word and, it means it's expressing and logic. And then you have the axon leaving out, and this is the terminal. So this neuron is an excitatory neuron. An excitatory neuron is a neuron that I have drawn in green. The ones in red are inhibitory neurons. So this is an excitatory neuron. That's why it's shown in green. It has only one axon terminal and is expressing and logic. This other one says BUF, buffer. It means it's just a buffer. One signal comes in and is being boosted out. Same thing we have here. We have another neuron here expressing and logic, but then it has 3 axon terminals. 1, 2, 3. It is also excitatory, and that's why it's green. But then this one is red, which means it's inhibitory. By inhibitory neuron, we mean that its contribution to the postsynaptic neuron is negative. That means rather than helping the postsynaptic neuron to fire an action potential, it is further preventing it from firing an action potential. So it's having a negative contribution to it. You can think of it as, why this is increasing the membrane potential, this one here, the inhibitory neuron, is decreasing the membrane potential further, making it harder to fire an action potential. Okay, and normally in neuroscience, we would say it is preventing that neuron from firing. All right. So this is another inhibitory neuron expressing and logic and has 2 axon terminals here. This is an excitatory neuron expressing all logic, having 1 axon terminal. All right. So this is a neuron. This neuron fires an action potential, and that action potential that it fires causes communication between this neuron and these 3 other neurons at the bottom. Never mind that I've drawn them as small neurons. I just wanted to illustrate to you that this makes contact with 3 other neurons. So the action potential here causes neurotransmitters to be released at the axon terminal that contacts these other 3 neurons. And by that way, this neuron communicates with these other 3 neurons. So I might draw it this way in our picture and say, here we have a neuron A contacting another neuron that may be, like this one is expressing AND logic, this one is expressing AND logic, and this is expressing AND logic. So this neuron A is contacting this other neuron that is expressing AND logic. In this place is contacting a neuron that is just a buffer. Here is contacting a neuron that is inhibitory and is expressing AND logic. And this neuron A is also contacting another neuron that is inhibitory, having 2 axon terminal and expressing AND logic. All right, so that's what I'm trying to illustrate here. So let's go into designing logic circuits. Now, before designing a logic circuit, the desired logic is usually expressed in a truth table, right? So before engineers will go to design a logic circuit, they first draw out the truth table. So here we have an exclusive OR truth table. So exclusive OR means it's either A or B, but it cannot be both of them. So we are saying that in our circuit, if A is 1 and B is 1, the output should be 0. For a neuron, that would mean that if A does not fire and B does not fire, then the Z, the postsynaptic neuron Z, will not fire. That's why it's 0. The second line says if A is 0 and B is 1, the postsynaptic neuron Z should fire. Here it says if A fires and B doesn't fire, then the postsynaptic neuron should fire. However, the last one is saying if both neurons fire, then the postsynaptic neuron should not fire. So how do we design a circuit like this? To design a circuit like this, we were going to show its logic gate representation and how it is done in using neurons. And that's what you have here. And I'm going to explain this diagram. So in this place, we have the truth table that we've designed in the previous slide. This is the truth table. This arrow is telling you that we are on this line now. This is where we are. So this diagram is showing that A is 0, B is 0, and Z is 0. Let's look at how it looks like on a logic circuit. In this logic circuit, we have 2 inverters. One inverter on input A and another inverter on input B. Then we have 2 AND gates. These are our AND gates and 1 OR gate. This is our OR gate. So when we have 0, 0, 0, 0, what we are saying is when input A is 0 and B is 0, indicated by a black line. This black line means nothing on this line is 0. So this is 0. So when A is 0 and B is 0, then the inverse of A, the inverting of A will give us a 1. That's why it's green. 1, 1. Same thing for B. Because B is 0, then the inverting of B gives us a 1. So you have 1 here, and that's why you see, and anything you tap from that place also will be 1. So this is 1 on this line, 1 on this line. So if you look at this AND gate, you have 1 coming in and 0 coming in. So the output of this AND gate will be 0. An AND gate, remember, an AND gate will only give out 1 when the 2 inputs are 1. So this 1 and 0. So that's why it's giving out 0, black. The second AND gate, 1 and 0. That's why we're having out 0, black. So when 0, 0 is feeding this OR gate, then the output will be 0. And that's what you have in this first line, 0, 0, 0. So this circuit is demonstrating what we have in this first line. Let's look at our neuron. This is the neuron on your left hand side. Two neurons, neuron A and B. You can see them. Look at the axon is leaving neuron A, making contact with this AND gate and this other buffer. So it makes contact with this buffer and makes contact with this AND gate. Neuron B also makes contact with this buffer and makes contact with the same AND gate. Now, this AND gate is actually an inhibitory neuron that has two axon terminals. So you have 1 and 2 axon terminals coming out from the axon of this neuron, this inhibitory neuron that is expressing an AND logic. So let's explain what happens. Because A and B are excitatory neurons, the buffer is excitatory, the two buffers are excitatory, and this is inhibitory. When nothing is traveling from A and B, everything just stays the same. There's no action potential that is firing from A and B, and as such, there's nothing coming out from Z. Let's look at a situation where you have action potential. When we move to the next line, look at our arrow. It's pointing on 0 and 1. That means A is 0, B is 1. The output is expected to be 1. So we look at this circuit and see if it does that. Let's look at this one, the normal logic circuit. So A is 0. So you see it's all black. B is 1. That's why B is green. The inverse of 1 is 0. That's why you have 0 here. The inverse of A, which is 0, is 1. That's why you have 1 here. When you tap 1 and 1, going to an AND logic, the output will be 1. That's why you see it's green. It's 1. In this other case, the second AND gate here, it's tapping from A and the inverse of B. The inverse of B is 0 and A is 0. So 0 and 0, the output will be 0. So you have the first AND gate on top, the upper AND gate giving you a 1 and the lower AND gate giving you a 0. When 0 and 1 enters into an OR gate, the output is 1. So that's why you see the output is green. Z is green. So in a digital logic circuit designed with logic gates, this is what we have. So this circuit is expressing what you have in this second line. Let's look at our neuron. In the case of our neuron, the star you see here at B means that B is now generating an action potential. So B generates an action potential. A does not do anything. Let's follow it. So this action potential is traveling from B. Watch it as it travels from B. It keeps going down. A does not generate any action potential, so nothing is happening at A. It keeps traveling, and then it branches off. So it travels while it branches off. The action potential is traveling. It gets to the first buffer and also gets to the AND gate. So you have 1 coming into the buffer. Because it's a buffer, it is going to generate an action potential, right? So it receives an action potential. It is expressing a buffer logic, so it will generate an action potential. So, but the AND gate, for it to generate an action potential, it needs both A and B to give it input before it can generate output. So because it's only B that is giving it input, the AND gate will not generate any output. Only the buffer will generate an output. So that is why you see that the AND gate does not generate any output, but the buffer will generate an action potential here, and we can follow that action potential as it goes, and it hits the Z neuron. Now, the Z neuron is an OR neuron, which means any input that is 1 will cause the Z neuron to fire an action potential. So, the buffer, the second buffer, is giving an action potential. It's firing an action potential towards Z. Z receives that action potential, and because it's an OR logic, it will also fire an action potential. So it gives out a 1. So this logic here is expressing what we have in the second column, where A is 0, B is 1, and the output is 1. So let's move to the third one. In this third one, we have A to be 1 and B to be 0. The best way to design this is just to reverse the two neurons, to relabel them. So rather than have A and B like we have here, I'm going to have B and A because it will do the same thing. It's just changing the names. It's just names that change. So there's no need following this because it's the same thing that happened in the second row that is going to happen in this place. It will go all the way out and then it will get to Z and it will fire an action potential. So let's pick the third one. In this third case, A is 1, B is 1. So let's analyze this circuit, the logic circuit that we have here that is built using logic gates. So A is 1, B is 1, which means A is green, B is green, showing 1. So you have 1 and 1. So that means their inversion will be 0. So the output here will be 0, the output here will be 0. When 0 taps into this AND gate and 1 taps into this AND gate, 0 and 1 will give us 0. Remember, it's an AND gate. An AND gate only gives you a 1 when the two inputs are 1. So one input is 0, the other one is 1, so the output will output 0. Same thing is happening in this second AND gate. One of the inputs is 0, one of the other input is 1, so the output is 0. When 0 is fed into the OR gate, then you have 0 coming out. And that's why you see that this circuit, expresses what we have in this last line, this last row, 1, 1, 0. So the output is 0. Let's see what happens with our neural circuit, the circuit we've designed using neurons. So A and B, A is 1, B is 1. So A is firing an action potential and B is also firing an action potential. Let's follow it. So the action potential is moving on the line, 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 moving along the axon, and now it reaches the axon terminal. So A, B are both 1. So the axon terminal, wherever they contact other neurons, they are going to fire action potential and trigger those neurons. So here, this is what we have. Now, the first buffer we have on top, because it's a buffer, it is also going to fire an action potential because it's just a relay. It receives an input and just relays what it received. So it's a buffer. The second one too receives an input and is just going to relay that output out. The second neuron too is expressing a buffer logic. So it will just receive input and then relay that input out. Now let's look at the inhibitory neuron. Two inputs are coming into this AND logic. The inhibitory neuron, the red neuron, which is inhibitory, that is expressing AND logic. So when two inputs come in, then that means the two of them are sufficient. It's an AND logic to cause this neuron to fire. So this inhibitory neuron is going to fire. So the buffer will fire, the two buffers will fire, and the inhibitory neuron will fire. So that's why you see that the three neurons fire an action potential. So when they fire, this action potential will travel along the axon and then it will move through to neuron Z. They will get to the terminal. Now, observe that because the inhibitory neuron has two axon terminals, it's going to contact Z with two axon terminals and two action potentials. We hit neuron Z. The action potentials will release neurotransmitters to neuron Z at two locations. So you can think of it. Think of the first buffer bringing in 1. The second buffer bringing in 1. But this neuron is bringing in -1 and -1, which means -2. So you are going to have a sum. Remember, we're doing a spatial summation. So you're going to have 1 + 1 - 1 - 1. The answer you are going to have here is 0. So two things are saying fire action potential. Two others are saying don't fire action potential. So they will cancel out. And so the Z neuron will not fire an action potential. So what you're going to have here is that Z will not fire because 1 plus 1 minus 1 minus 1 will be 0. So Z will not fire an action potential, and then the circuit will just remain like this. So you can see that the circuit we have on our left-hand side is equivalent to the circuit we have on our right-hand side. So it's just that the one on the right-hand side is designed using logic gates, which we use to design computers, and the one on the left-hand side is designed from neurons, which are the building block of the brain. So normally the logic circuit we just talked about that we design using logic gate has a special gate, its own type of gate that is called an exclusive OR gate, and it's shown like this. So I just round up the entire of that circuit into this small specialized circuit called an exclusive OR circuit. Thank you very much for listening, and see you at another time. Bye.